Professor R. Asokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
We have been going through a course of lectures on crystal structure. In this lecture, the contents are as follows: atomic packing factor or fraction of simple cubic, body centered cubic and face centered cubic structures. And in the case of simple cubic structure, as I told you in the last lecture, in the case of simple cubic, you will have atoms at the corners of the cube. I will show you in a moment the model on the crystal structure of simple cubic as well as the face centered and body centered cubic structures. Now, this one is the simple cube. You know, it is called simple cube because you have a cube wherein at every lattice point you have an atom, right. It is one of the 14 lattices which we have been discussing with regard to Bravais lattices. This is a simple cubic structure, right. Unfortunately, nature does not allow many materials to crystallize in this simple structure. As I told you in the last lecture, alpha polonium is one of the unique examples of a material crystallizing in the simple cubic structure. So, you have an atom here, atom here, atom here, atom here and so on. You have got 8 corners, obviously for any cube there will be 8 corners, and you have got atoms at the corners. This is called the simple cubic structure. So, this is a cubic unit cell. This has to be repeated, right. You have the simple cubic structure, then you repeat this and you repeat this, then you get the whole crystal or the whole lattice, right. You have to repeat. This is the fundamental building block, right. And as I told you, the rare only alpha polonium has this structure, and when we are trying to calculate the atomic packing factor, we make use of what is called a hard sphere model. Now, before that I will go through what is called coordination number. What is meant by coordination number? It is the number of nearest neighbors. As I told you again in the last lecture, you have got an atom here, atom at the top, bottom here, and then 4 in the same plane. So, there will be 6 atoms which surround this atom. So, for this atom the coordination number is 6. You know, every lattice has got translation invariance, whether you take this atom as the origin or the reference atom or this as the reference, you look at the whole structure. Any atom can be taken as the reference, because every atom is equivalent to every other atom. Okay. Any atom can be taken as the reference. This is the atom which you are talking about. You have it here. There are 6 nearest neighbors. What is the atom I am talking about now? I can have this as the origin, I can have this as the atom under consideration. So, with respect to this, you have got at a distance a, you have got atom here, at distance a, I have got atom here, distance A I have got atom downwards, right. How many? You have got 1 here, 2 here, 3 here. Suppose I call this the x axis, then on the negative x axis there will be one atom here at distance same E, you have got another atom here, and similarly along this direction there will be one atom here. Suppose I call this the y direction, along minus y there will be one atom here. So, that makes the fifth atom. Similarly, along the z direction, right. I got one atom here, then along this direction there will be one atom here, right. So, with respect to this atom I got 1 here, 2 here, okay, then 3 here, 4 here, 4 will be the same plane, right. 1 above, 1 below. This is the one that I am having here, 1 below and 1 above. So, for this atom the coordination number is 6. Similarly, for any other atom the coordination number will be the same 6. This should be borne in mind with respect to simple cubic structure. So, the coordination number should be known. For every structure the coordination number should be known to calculate the packing factor. Then we make use of what is called the hard sphere model. As I told you, you fill up the box, fill up the cell by means of hard spheres. What I mean by hard sphere means, instead of having 2 atoms separated by this distance A, you assume this to be a hard sphere coming up to this, right, up to A by 2, and another sphere coming with a radius A by 2. The 2 spheres will be touching each other. This is for calculating the packing fraction or calculating the extent to which the unit cell is filled up by the atom or by the atoms. You make use of what is called a hard sphere. I make use of the words hard spheres. The atoms are assumed to be hard spheres touching each other. In reality, the atoms cannot be touching each other. Can you tell me why the atoms cannot be touching each other? If the atoms are touching each other, what do you have an atom? You got the nucleus and the electrons. If 2 atoms are touching each other, the electrons of the 2 different atoms, the electrons will be repelling each other. So, in reality, no 2 atoms in any solid, right, any solid, whatever be the bonding, no 2 atoms can be touching each other. And you all know about Bragg's law, n lambda 2 d sin theta, and so you have got d spacing, right, and also using d you calculate the lattice parameter. This is called the lattice parameter, distance that separates the 2 atoms. So, in reality the atoms will not be touching each other, but for the sake of calculating the atomic packing factor, we are assuming the atoms to be hard spheres touching each other. And again, what is the radius of the hard sphere? That will be A by 2. So, if this is A, I assume this atom instead of a point particle, if you have got an atom with a red ball, I assume this atom to be a hard sphere which is having a radius. This is A by 2 is here, with up to A by 2 this will be a sphere, and this will be again A by 2 this is a sphere. And so, the 2 spheres, the radii, the sum of the radii of the 2 spheres will be equal to A, right. So, 2r will be equal to A. So, we want to calculate the maximum packing density. The atomic packing factor is defined as the volume occupied by the atoms or the volume occupied by the hard spheres by the volume of the cell. What is the volume of the cell? If A, the length of each side is A, the volume is A cube, right. All of you know the volume is, for any cubic structure the volume will be A cube. Now, we have to calculate the volume occupied by the atoms. Now, how many atoms you can associate with this cell? That is the question. You may say that there are 8 atoms, but the effective number of atoms that you can have per cell will not be 8, because this cell you have got atom here, and if you have got another cell here, right, assume this cell also is simple cubic. You forget about the presence of these atoms at the phase centers, you assume this to be a cell which is identical to this, right. You have to forget about the other atoms. You should assume you should look at the atoms found only at the corners, 8 corners. So, you got whatever I am showing this, because when you have this like this, right, this atom will be a common point to these two unit cells, right. So, this becomes a common point. Similarly, if you have got, I will have another cell here, right, another cell here. Now, therefore, if I take this cell, this will be a common point for this and for this, and you will have another cell here, a common point, this will be a common point for this cell and this cell, and similarly this is a common point for this cell and this cell. So, in the same plane there will be 4 unit cells which will be coming into contact, and this will be a common point to all the 4 cells, and above this I can have one cell, right. So, this will be a common point for the 5th one, and again 6th one, then I will have 7th one and 8th one. Now, what I would like to tell you is I can have 8 cubes, one here, 2 here, 3rd one here, 4th one here, 8 cubes, 4 cubes, and above that I will have another 4 cubes, is that right. So, you got one unit cell, second unit cell, and the third one will be here, for this also a common point, 4th one will be here, a common point, then above that I will have 5th one, 6th one, 7th one and 8th one, right. So, this will be a meeting point of 8 cells. If this lattice point, so this lattice point actually is shared by 8 adjacent cells. The point to be understood is each and every lattice point in simple cubic, or each and every lattice point at a corner of a cube is a point where 8 cells join each other, right. When 8 cells are joining each other, the contribution of that particular atom to the cell will be only 1 by 8. That is important point to be understood. So, when I am talking about the APF, which I define as the volume of the atoms in the unit cell divided by the volume of the cell, the star shows that we assume the atoms to be hard spheres. That is the reason why I make this A to be equal to 2 R, or R will be equal to A by 2 or 0.5 times A. What do you understand by this? This atom is not considered to be a point like this, another atom here is not considered as a point, but the atoms are made to touch each other, and each atom is having a radius R, which will be equal to 0.5 times A. 0.5 times means half of A, right, this A, and so this A will be equal to 2 R, or R will be equal to A by 2. Okay. The number of atoms per unit cell, as I told you, it is 8 into 1 by 8, that is important. I showed you each and every lattice point is a common point where 8 cells meet, therefore, the contribution of every lattice point at the corner to the cell will be 1 by 8. Okay. That is important point. So, now what are the things that you know? The number of lattice points that you can associate with simple cube is 8 into 1 by 8, that is 1. So, the effective number of lattice points for a simple cubic will be only 1, that is one point. Second thing is the cell dimension or the lattice parameter A will be equal to 2 R, because your the radius will be equal to A by 2, this radius of the hot sphere will be equal to A by 2. So, your 2 R will be equal to A, or R will be A by 2. Okay. Therefore, you have to put these things now. The effective atoms per unit cell, as I told you, only 1. For simple cubic, how many atoms you have got for simple cubic? The effective number of atoms or lattice point will be 1. Okay, 1. The volume of the atom will be 4 by 3 pi into R cube. What is R? R is 0.5 times A, right. Is that understood? So, the radius is half of the cell dimension, okay, because you are assuming the atoms to be hard spheres. So, you have 4 by 3 pi into 0.5 A cube. The cell volume, as I told you, for any cubic structure will be A cube. So, you can cancel this A cube with this A cube, and you are left with only the constants 4 by 3 into pi into 0.5 whole cube. So, that gives them atomic packing factor, that works out to be 0.52. What does it mean? only 52% of the cell volume is occupied by the atoms. So, when you have the simple cubic structure, only 52% of the space is occupied by the atoms. The two important factors which I have been mentioning about the calculation of packing fraction or the packing factor are the following. One is, for any given cell, the effective number of atoms you have got per cell should be known. That is, the effective number is 1 for the simple cubic structure, and then you should have a relation that connects R and A, right. So, that you can cancel these two. The volume comes in the denominator, you have to express the radius in terms of the lattice dimension A in the case of cubic structures. Now, in the case of cubic structures, the two atoms will be touching each other, therefore, your A will be equal to 2 R, or R will be 0.5 times A. So, A cube and A cube can be cancelled, and so you are left with only the constants that you have here, that comes out to be 0.52. That implies only 52% of the cell volume is occupied by the atoms, right. 48% remains empty. Okay. This is a relative understanding of the packing density. As I mentioned to you earlier, it is not really true to assume the atoms to be like hard spheres, because the simple reason that the atoms, after all, containing electrons cannot be touching each other, because electrons will repel each other, the Pauli principle and other things come. Okay. So, what we have done is we have calculated the packing factor for a simple cubic structure. Now, we will move on to the body centered cubic structure. What is the difference between simple cubic and body centered cubic structure? In the case of simple cubic, you have got atoms only at the corners. On the other hand, in the case of body centered cubic structure, you will have an atom at the center, in addition to having atoms at the corners. You have got atoms at the corners, right. In addition to that, there will be atom at the center. There are number of solids which are crystallizing in the body centered cubic structure, unlike the case of simple cubic. In simple cubic, alpha polonium, as I told you, is the only known example. On the other hand, as I will be showing at a later stage, there are number of solids in the periodic table. You can see the several elements, right. The elemental structures crystallizing in the body centered cubic structure, wherein you find atoms at the corners. In addition to the atoms at the corners, you have got atom at the center. So, you have got an atom at the center of the body, right, center of the cube. That is the reason why it is called body centered cubic structure. Okay. Now, how many atoms will be associated? You will be associating with this unit cell. As I told you, if you got atoms at the corners, 8 corners, then 8 into 1 by 8 will be 1, and there is one atom at the center. The atom at the center of the cube is not shared by the adjacent atom. There will be another cube here. This is not shared by the unit cell here, or this is not shared by another unit cell you will be having here, or another unit cell you will be having here. So, this atom which is at the center wholly belongs to the cell. Okay. The atom belongs wholly, the atom is associated with the cell. Therefore, it will be 8 into 1 by 8 plus 1, that will be 2. So, the effective number of atoms or the lattice points you can associate with the cell will be 2. Okay. That should be remembered. Second point is, what is the coordination number? In the simple cubic, I told you the coordination number is 6. For the body centered cubic, what is the coordination number? As I told you, you can take any atom as a reference atom. The simplest thing will be, you take that, you look at the atom at the center, right. So, if you look at the atom at the center, the number of nearest neighbors are obviously 8, right. You got atom at the center, all the 8 atoms which are found at the corners are equidistant from the atom at the center. So, the coordinate number for body centered cubic structure will be 8. That is what I have given here, the coordinate number is 8. That is one thing. It is a closed packed note, all atoms are identical, the center atom is shaded differently only for the ease of viewing, right. It is not necessary that these atoms are different, only for viewing you got white colored. Maybe in the case of iron, iron is solid crystallizing the body centered cubic structure. So, all the atoms, this atom here, this iron, there are iron atoms at the 8 corners, the atom at the center, right, atom at the center, then the atoms which are found at the corners. Okay. The atom at the center wholly belongs to the cube. How do you calculate the atomic packing factor? You have the well known relation, the volume occupied by the atoms in the unit cell divided by the volume of the cell. When you want to calculate the volume of the atoms, then you should be knowing how many atoms are there. I told you in the case of body centered cubic, you have got 2 atoms, right. How many atoms are there? 2. 1 here, 8 into 1 by 8 plus 1, right. 8 into 1 by 8, that is the atoms at the corners, and then apart from that, in the body centered cubic, you will be having 1 atom coming from the cube center. The center of the cube you have got an atom. So, 1 plus 8 into 1 by 8, that makes your 2 atoms per unit cell in the case of body centered cubic, and again the length will be 4r, that will be root 3 times A, right. Okay. This is the relation that connects the radius and lattice constant A. That is important in every calculation that you make regarding packing factor. You have to see that A and A are cancelled in the case of cubic structures, right. Now, anyway, you have to get a constant value number. So, you have to express R in terms of A and vice versa. You will be having here A and R, you have got R will be this much. Here again the atoms will be touching each other, the atom will be touching here and the atom will be touching here, that in the hot sphere approximation the atoms will be touching here. So, the A will be equal to your 4R will be root 3 times A, right. Now, so in the case of 4 by 3 pi r cube, R will be root 3 by 4 A cube, right. Using these two, you find that your R will be root 3 by 4 whole cube, that is what you have here. So, the number of atoms is 2 into 4 by 3 pi into root 3 by 4 into A to the power of 3, that gives the volume occupied by the 2 atoms. Now, what is volume of cell? That is same A cube. So, you are substituting A cube here. If you now you can cancel this A cube with this A cube, you are left with the constants 2 multiplied by 4 by 3 pi into root 3 by 4 to the power of 3, that is what you have, right. That gives you a value 0.68, that is the atomic packing factor for a body centered cubic structure will be 0.68. What do you mean by that? 68% of the cell volume is occupied by the atoms, when the atoms are assumed to be like hard spheres, 68% is occupied, right. When compared to simple cubic, the packing density is much higher in the case of body centered cubic. Obviously, it should be there because there is one extra atom here. So, the packing density will be higher. Let us now move on to another cubic structure. With regard to Bravais lattices, we talked about cubic structure. In the case of cubic structure, there will be 3 kinds of cubes. One is simple cubic, the other is body centered cubic, third one is the face centered cubic structure. This is the so called face centered cubic structure. So, let us now move on to a face centered cubic structure. What you find is you have atom at the faces, right. In addition to atoms at the corners of the cube, 8 corners are there, then there will be atoms at the face centers. How many faces are there for a cubic structure? There will be 6 faces. So, there will be atoms at each, you got an atom at each face, right. At the center of this face you got an atom. That is the reason it is called face centered cubic. This is a face, right. This is another face. There are 6 faces, right. You got an atom at the center of the face, right. This is a body centered at a body center, right. This is a body centered cubic structure. You at the center of the cube you got atom, but wherein here you got an atom at the face, right, face center. You got an atom at the face center, this face and similarly this face, right. Okay. There are how many phases? 6 phases are there, and so you got atoms at them 6 phases. Now, let me ask the question, now what is the contribution to the unit cell coming from all these atoms? As I told you in other cases as well, it is you cannot take all the atoms to be equal to the effective number of atoms that can be associated with the fundamental unit cell, right. So, as in the earlier cases, you got atoms at the corners, there are 8 atoms at the 8 corners, and so the contribution coming from the atoms at the corners will be 8 into 1 by 8. What about the atom here at the face center? Atom at the face center, if you look at the atom at the face center, there will be another cube here, right. So, will be another cube, identical cube, that also will have, okay. So, the atom at the face center, that will be common to this unit cell as well as to this unit cell. So, the contribution of this atom is equally shared by this cell and this cell. So, the contribution of this to this will be 1 by 2, right. Is it understood now? Because this atom, something like you have a wall, you got atom here, this is one room, then another room, right. Something like a cell here, another cell here, maybe in jail you got a cell, right. So, you got a cell, another cell, there is a wall here, you got atom at a wall. So, it will be partially shared, it is equally shared by the cell here and the cell here, right. A cell here and a cell here. So, this is a common atom for both the adjoining cells or adjacent cells. Now, therefore, the contribution of this atom to this cell is half, the contribution of this to this cell is half, right. Let us not worry about, you take one of the cells, right. So, the contribution coming from this atom is half. There are 6 such atoms at the 6 phase centers. So, the effective contribution coming from the number of atoms will be 6 into half, right. The unit cell contains how many atoms? As I told you, 8 atoms at the corners, each atom contributing 1/8 to a unit cell. As I told you in the case of simple cubic as well as the body centered cubic, this is also true for the face centered cubic structure. Okay. Then apart from that, the atoms at the face center, they contribute, there are 6 atoms at the 6 face centers, they contribute half of each atom. So, 6 into half, that makes 3 plus 1, that may be, that means that there are 4 atoms per unit cell. Okay. There are 4 atoms per unit cell, then you know this will be a by 2. Okay, these atoms will be touching each other, right. So, the atom here will be, they all will be touching each other, and so the phase diagonal, okay, the phase diagonal is how much? A into root 2, A is here, A into root 2 will be the phase diagonal, root 2 into A will be here, root 2 into A will be equal to, this is 2 r, right. If r is the radius of the atom, r here, 2 r here, r here. So, 4 r will be root 2 into A, right. The length of the phase diagonal will be root 2 into A, right, the phase diagonal. If A is the length of the unit cell, the length of the dimension of the phase diagonal will be root 2 into A, that now contains a atom here, a hot sphere kind of atom with a radius 2 r, another r here, another r here. So, r here coming from this atom, r here and 2 r here, r plus 2 r plus r. So, that is 4 r. 4 r will be equal to root 2 into A. Okay. There are 4 atoms. So, and now you can as you have done in the earlier case, 4 atoms are there, 4 times 4 by 3 pi into your the connection between these two will give you your R to be equal to root 2 into A by 4 to the power of 3. So, substitute all these things, cancel A cube with A cube in the denominator and the numerator, and so you are left with the constants that will give you this following number 0.74. The APF value for the face centered cubic structure will be 0.74. It means 74% of the cell volume is occupied by the unit cell. Let me now summarize as to what we have learned from this lecture. The atomic packing fraction is defined as the ratio between the two parameters, volume occupied by the atoms to the cell volume. Okay. Second point is about the coordination number. Coordination number refers to the number of nearest neighbors. Using the coordination number, we have calculated the atomic packing factors for cubic structures. The atomic packing factors for simple cubic, body centered cubic and FCC structures are 0.52, 0.68 and 0.74, or in other words 52%, 68% and 74%. Let us now pass on to the question session. What is meant by coordination number? The question 2, what are the coordination numbers for the cubic structures, simple cubic, body centered cubic and face centered cubic? Then obviously, what are the APF values for the cubic structures? With this we come to the end of this lecture. In the lectures to come, we will see the other structures which we come across with regard to crystal structures. Thank you.